Hello, everybody. Here I am, Isabel Paz Niño Mayorga, this time re-recording a talk that I delivered only this week. Although I tried to take into account all the tech that I needed, my microphone failed. But I think that sharing what I've prepared for this talk is really important. And I'm doing it now on my own for you to watch. And I've got a proper mic, and hopefully everything will be all right. This talk was organized by the EDI committee at the Manchester Institute of Biotechnology and the Department of Chemistry at the University of Manchester, where I was invited to deliver a talk about my background in the chemical sciences, but also my lived experience. And for me, it was a truly honor to be there to share my experience in academia coming from a global south country, Ecuador. This is where I was born, right on top of the equator line in South America, with lovely weather and beautiful landscapes all year round. I was born in a lovely family of three. My mom and dad always encouraging me to explore new things. I'm there finishing and achieving my first academic milestone, that was finishing kindergarten, and then exploring some other passions that I had, that was dancing and music. Then my academic journey in chemical engineering started in Ecuador. I studied at Escuela Politécnica Nacional in Quito, the capital of Ecuador, and here I am with some of my friends doing some labs. But the picture you see on the bottom brings really nice memories to me, because this was the first time I put a foot inside an industrial site. It was inside of an internship I did after I finished my second year of chemical engineering. And for me, it was amazing to be able to see for the first time a real heat exchanger, or even going inside a cooling tower. Until then, all this equipment were only shown as boxes when I was studying. And it's worth saying that with my mom, she was a nurse in the health sector. My dad, he was a school teacher. And in my extended family, I really didn't have a role model for engineering. And when I started my degree, I didn't know what chemical engineering was. I discovered this when I started my second year, when I had my first lecture in mass and energy balances, when I knew the difference. And I liked what I saw, and I carried on in my career. This picture here brings very special memories for me, because first of all the young ladies you see there wearing beautiful Ecuadorian traditional dresses. They are all chemical engineering students. And studying in a very intense university, engineering, it was very difficult to sometimes carry on with passions that you have. And with a couple of friends, we founded a dancing group. This taught us something, that we can combine thought engineering or STEM subjects with passions that you have. In addition, this picture was taken inside an international event. It was a chemical engineering students event for all Latin America. This time was hosted in Ecuador, in a city called Loja in the south of the country. Until then, that was the longest trip ever I had inside my own country. That was about 12 hours by bus. And I met amazing people from different countries. On that occasion, I told myself, my career will help me travel the world. And guess what happened? The year after, I traveled to Mexico, still as a chemical engineering student, to participate in the next edition of the International Congress of Chemical Engineering Students. This time, I've expanded my network with fellow chemical engineering students from Mexico, Guatemala, Argentina, and many other countries. In 2012, I finished my degree, and soon after I started my first job, which was inside a cement company. I was the new product development engineer, and this first position had a few challenges for me, being a young, recent graduate and a young, recent graduate chemical engineer going into industrial side brought specific challenges. And the picture you see there is very important, it's very interesting. It's inside a rotary kiln that was under maintenance, changing the refractory material. After a year or so, I moved to another institution. This was a government-funded research institute dealing with mining, gold extraction, environment, and everything around geology, for example. And this project was focused on improving the working conditions of artisanal miners. And the picture you see on the left, this mountain has lots of gold inside. So it's rich. But what you see on the surface is not the same. The conditions where the artisanal miners were working were very poor, and we were there as a research institute trying to help them improve their conditions to reduce the impacts in their health, in their environment, and also for their income. After some time, I decided to go and study abroad. That is when I started studying my master's degree at the University of Manchester. And when I finished this degree, I returned to Ecuador. And I started working in two Ecuadorian universities, supporting a range of modules in engineering. Then, after 3 years of teaching, I realized I enjoy a lot teaching. I was preparing myself, studying, trying to stay on top of what is available for chemical engineering. And then I realized it's time for me for a PhD. I can do it. I want to do it. And I moved back to the UK in 2019. This time I didn't come alone. I came with my husband. We both are chemical engineers and started together our PhDs. During this time, there was a time that we had to socially distance and wear face masks. Some of you may remember, but finally, I reached the end of my PhD, and this is the day of my viva, where I was 37 weeks in my pregnancy. And for context, a pregnancy lasts about 40 weeks, so I was very close. This was the day I became a doctor, and this is the day I became a mom. A life-changing event, I must say. In the same year, in 2023, I started my current position at the University of Manchester inside the Sustainable Process Intensification Group. And at the heart of our research, we study chemical looping. I'll tell you a bit more in a few slides. And thanks to technology, I'm very grateful that I'm able to continue contributing to my country, delivering a series of guest lectures at one of the top universities in Ecuador. A quick ad talking about chemical looping. The largest event that gathers all chemical looping researchers, is happening in Manchester this year, and we are very proud and excited to host it. And keep an eye if you are likely to attend or interested to know more about chemical looping. Manchester will be welcoming you very soon. Coming back to the research work that I've done since the start of my appointment, I started working in the Recycle project, and this was funded by the UK government. And at the heart of this technology is chemical looping reforming with the purpose of producing low carbon hydrogen. In August 2025, I started a collaboration with the Tyndall Center in a group dedicated to the study of climate change. And we are studying routes for decarbonization of transport. Why I'm there? Because I work in fuels. That will be my contribution. Only in November last year, we kicked off another project, this time EU funded. And again, this has at its heart chemical looping, this time to use CO2 for the production of liquid fuels. And finally, Electra, also EU funded, that is a project that we will start next month, will develop new technologies, particularly electrically driven reactors for ammonia cracking and reforming. Now, what is chemical looping? Let's get started with a simple combustion reaction that most of us are familiar with. We have a fuel, oxygen, and this reaction produces heat. That is our main product. That's the objective of a combustion reaction. But we have side products, CO2 and water. And guess what? CO2 is the one that is responsible for climate change. Now, chemical looping, how this works. The combustion reaction is now split into two reactions. The first, metal, and now the source of oxygen is a solid material called metal oxide. We produce CO2 and water and a metal because we have removed the oxygen. This is the reduction reaction. Then we have oxygen and we reuse the metal that was produced in the first reaction and produce heat. That's the target product in the first place. And we obtain again our metal oxide. This is the oxidation reaction that is exothermic and hence the production of heat. We have our metal oxide ready to go for another cycle, and that's why this process took this name, chemical looping, because it can go from reduction and oxidation and continue this cycle. This metal oxide is typically on a support that is inert, and in general, this solid is called oxygen carrier, something to keep in mind. Now, we have looked at the reaction, the stoichiometry. Now let's look at a conventional reactor. For combustion, again, we have as an example methane as a fuel, but oxygen is typically not used pure because it's expensive. We will need an air separation unit, and having pure oxygen will also lead to extremely high temperatures, which are also prohibited inside a reactor. Hence, we use air, we produce heat required, but then here's where we have the issue. We produce CO2 and water or side products, and nitrogen is still there. It's an inert that is mixed, and then we have this mixture that is difficult to separate. And if we don't recover the CO2 produced, then this is released into the atmosphere and contributes to global warming. And that's the advantage of chemical looping, because we split the combustion reaction into two. Again, we have the fuel reactor, that is the reduction stage, where we feed methane and metal oxide, and then we obtain CO2 and water. And this mixture here is very very easy to separate. The metal is solid, and CO2 and water can be separated only using a simple condensation of water. Then the metal goes to the second reactor, where we have it reacting with air, produce heat, and then the metal oxide and nitrogen are again easy to separate. Hence, we are not contributing to climate change. We have a production of pure CO2 in one side, is another product, and heat. Now, looking at configurations of industrial reactors, the first option and the most used at the moment for chemical looping is the fluidized bed, where the solid material, the oxygen carrier, travels between the air reactor and the fuel reactor. And we have continuous inlet and outlet of gases. Another configuration, and that's the one at the core of the research we do at the University of Manchester, is impact bed reactors, where the solid material, the oxygen carrier, is stationary inside it. And we use it, we feed, for example, air until the solid material is totally consumed, and then we switch the valves to change the feed. There are advantages and disadvantages of both configurations. I'll start with the advantages of the fluidized bed, that obviously it's a continuous process. As you can see, all the inlet and outlet streams. Whereas for the packed bed operation, this is a dynamic process. And the challenges we will need to face with operation and control is something that we need to work on. Another characteristic that is important for packed bed reactors is the ability to work at high pressure, something that is quite challenging in a fluidized bed. And this is an advantage because this increases the operating window, and we can explore other operating conditions that can enhance our reactions. And finally, regarding the solid material, the oxygen carrier, in the fluidized bed, the continuous movement around the two reactors can promote degradation due to attrition, that we can lose some of the solid material as in the form of fines or powders. Whereas in the packed bed, the solid material is stationary and we don't face this problem. And this will tell us that the solid material can last for a bit longer. Now, the recycle project. The first project I worked in the Spring Group. This project had 6 work packages, let's say 6 teams focusing on different aspects of the technology. We have, for example, process components, that is looking at development of oxygen carriers at lab scale using a range of lab scale reactors. Prototype design and construction, that did all the work that then realized in the construction of a pilot plant that is soon to be started at Manchester. We have also the industrial application section, that's me. I'm the modeling and simulation person that use these tools to study different applications at different scales for this technology. And we are very excited to see the pilot plant operating to check some of the assumptions we have made in our simulation work. And we have some other work packages that includes exploitation, dissemination, and communication, that is sharing with the public the findings of the research, and obviously the management to make sure the project is road to completion. What is the recycle technology? It's a modular chemical looping process that happens in high pressure adiabatic packed bed reactors that have the solid material, the oxygen carrier, in a vessel that is reactor. As I mentioned before, this is a dynamic operation, but this one contains three key stages. The first, that I already told you a little bit about, that is oxidation, where we have a gas-solid reaction. We feed air, oxygen from the air reacts with the oxygen carrier, and this reaction is exothermic. The heat produced by the reaction is retained in the solid material, whereas the nitrogen exits the reactor. We switch the feed. Now with reduction, where we feed an off gas. An off gas is a low-grade fuel that should contain certain amount of reducing species, say methane, CO, hydrogen, that react with the oxygen carrier to produce CO2 and water that are easy to separate and still retain the heat that was produced in the oxidation reaction, because these reactions here, the gas solid reactions, are a combination of endothermic and exothermic, and the temperature is kept relatively the same. But the third step, that is something interesting, and I haven't told you about yet, is a reforming reaction. This is a catalytic reaction where the solid material acts as a catalyst, and we can have different type of reactions such as steam methane reforming, dry methane reforming, water gas shift, where we feed methane and steam, and the reforming reactions are endothermic, and the heat to drive this reaction is taken from the solid material. Once these reactions occur, the bed is cooled down, producing syngas, that is a mixture of CO and CO and hydrogen, and the bed is cooled down and is ready for another cycle. The recycle technology is flexible in both sides in terms of the feedstock and the products. In the feedstock side, it can use a range of liquid and gaseous feedstocks. And in terms of products, we have one stream of pure CO2 that can go to storage or for further use, and syngas that can be used in a range of applications. I will focus on the ones we evaluated during the recycle project. The first is the production of hydrogen, where you see here the three key stages: oxidation, reduction, and reforming, and the feeds, natural gas and steam, that are combined and fed to the reforming reactor that uses the heat that was retained in the solid material. We produce syngas, and then it goes to a water gas shift reactor to improve the hydrogen to CO ratio. Then it goes to a pressure swing absorption unit to separate hydrogen as a product, and the tail gas that contains still some hydrogen, CO, CO2, methane that has not been reacted previously. It returns as a low-grade fuel on off gas to the reduction stage to remove the oxygen from the oxygen carrier, producing CO2 and water that goes to a CO2 drying and conditioning steps. We have water that is removed and CO2 as a product. The oxidation step, where we have air in, oxidation, oxygen trapped, and then nitrogen out. I studied this configuration at two different scales, 600 megawatts and 2 megawatts. 600 megawatts, if to get an idea, that will be the energy required by a city the size of Manchester, to provide energy to homes in Manchester, and 2 megawatt will be for the size of a small town in a day. We also evaluated the recycled technology, this time to produce syngas as a reducing agent for the steel industry to produce direct reduced iron in a shaft furnace. Typically, steel is produced using a blast furnace, but it has the production of CO2 there and needing a downstream CO2 removal. But with this option, what we have is we are decreasing the amount of carbon that is fed to the process, to the steel process, and we produce the direct reduced iron, and the top gas, that will be a low-grade fuel, is returned to the recycle reactors for the reduction step. Again, we have CO2 with high purity as one of the key products. Another application is the use of syngas from recycle for methanol production. An important note about this process is that we use biogas instead of natural gas, and this was a way to valorize biogas because it contains a significant amount of CO2 that reduces its calorific value. In addition, another advantage is that the methanol process occurs at very high pressures, and the recycle process can operate at high pressures too. So if we already have a syngas produced at high pressure, then the energy required by the compressors prior the methanol plant will require less energy, and hence we have an advantage for the downstream operation of the methanol plant if we use syngas production at high pressure. Only a key results about the recycle case studies. Overall, the energy efficiency is relatively high compared to other technologies, and the energy efficiency compares the amount of energy obtained in hydrogen to the amount of energy fed, and that is the natural gas and the electricity used. The coal gas reforming efficiency is relevant for hydrogen production only, and these values compare very well with traditional reforming technologies such as steam methane reforming and autothermal reforming, where recycle outperforms their efficiency. And finally, the CO2 capture rate, that in all cases is over 99%, and it tells us the ability to capture the CO2 that is produced. And if we compare this with traditional or conventional absorption processes that are currently used for CO2 capture, this technology outperforms the traditional technologies. There are still things that need to be addressed, and as the future work, we still need to work on operation and control strategies to deal with a dynamic process. And during the development of this technology, we identify key areas for development for materials. One is the oxygen carrier that has several aspects that can be improved. One of them is the cost. It should be robust, and also the ability to support cycling changes in temperature. Valves, I show you one of the pictures that this is a key component for the technology, and valves need to stand severe conditions for operation, that is pressure, temperature, and also frequent opening and closing. So there is a need to develop robust valves that can operate at these conditions. And also another component is the refractory material that again needs to stand with cyclic changes of temperature. This is it about me. All my bachelor's, master's, and PhD in chemical engineering, but I also wanted to share the other side. And that is an interest in communication. Now for me, that's a passion. Since I was a kid, I remember I was the one that wanted to talk in family reunions. And when I came to Manchester, I discovered Toastmasters. That is an international organization that is dealing with and trying to contribute with the development of leadership and public speaking skills. I joined Manchester Communicators, my Toastmasters club, more than 4 years ago. And this has given me the opportunity to meet amazing people from all different backgrounds and even be part of amazing projects. Only recently, I was invited to participate as a panelist talking about inclusion. That was a very exciting and interesting event, listening from different perspectives, different people, and having the opportunity to also share my experience and my views on what it takes for us to improve equality, diversity, and inclusion. Science communication is something I have very close to my heart. And a bit of a background, I told you about my family, where in my close and extended family, I really didn't have a role model for engineering when I first decided to select chemical engineering. But since I was a kid, I was inclined to STEM. And I have to confess, it had to do a lot with a TV show I watched when I was a kid. It was called The Big Man's World. And I loved the show. And I imagine myself doing those same demonstrations sometime to inform and inspire the future generation of engineers and STEM professionals. And that can be done through science communication. The first time I had the opportunity to get involved with science communication was through Pint of Science as a volunteer, supporting the delivery of two shows during the pandemic in 2020 and 2021. But then I was on the other side when I competed with science communication, sharing my research for an extended audience or a non-technical audience. And the first was the 3-minute thesis competition that is known worldwide. And it offered a range of training, and it was a very exciting opportunity to look at. This is open for PhD students. And then FameLab with a similar format as the 3-minute thesis, but this is open for researchers in any career stage. And I totally encourage you all to take the opportunity and the chance to participate in these competitions, enjoy the process, and share your science. Another event that I had the opportunity to contribute to was at the Instituto Cervantes to celebrate the International Day for Girls and Women in STEM. Again, talking about different perspectives and life experiences to inspire the future generations. And when you start to say yes to things, amazing things happen. And one of them was that I was invited to a radio show to share my experience, something similar as I'm doing today, but in a conversation mode, where obviously I talked about my experience with cement, with gold extraction, and I had very curious questions for the lovely host of the Somos con Cecilia Ramos show, that is a Spanish speaking radio show in Manchester. After this show, the feedback was amazing. People liked what they heard, and this led to an amazing project that I'm very excited and very proud of. My very own science dedicated segment called Somos Ciencia con Isabel Pazmiño inside the Somos con Cecilia Ramos radio show. For me, this is like a dream came true. I've had a chance to expand my community and get to the Spanish speaking community in Manchester and beyond through this program, sharing topics of interest. For example, chemistry versus chemical engineering, something I wish I had heard when I was younger. Now I am in the other side with the ability or the opportunity to share and educate and inform others. I'm going to make a pause because I need to take some water. Excuse me, I am back. And let's carry on with the science communication. And this comes to public engagement and outreach. Is going out there, bringing the science to other people. And I've done this through STEM Ambassadors, that is a UK wide network of people from academia and industry bringing the science, everything related with STEM to school, colleges, and museums. With this, I've been very happy to be part of the exhibition of my favorite museums in Manchester, and also through the university, who has excellent opportunities to get our science out and about. This is me, Isabel Pazmiño Mayorga, with a PhD in chemical engineering, all my bachelor's and master's as well, industrial experience of 2.5 years, research experience of over 8 years, teaching in higher education for more than 4 years, 6 publications, more than 10 conference contributions in different countries, and I'm an enthusiastic science communicator in training. Everything goes very well on my CV, but this is only the tip of the iceberg. What lies beneath the surface? And for many of you in academia, this may resonate. How many of you have ever had a failed experiment, a broken machine in the lab, a simulation that simply refuses to converge, a failed job application, an unsuccessful grant or fellowship application? All of this teaches something, shapes us as researchers, but they don't make it into our CV. And for early career researchers, we are often in short-term contracts, and these are time-limited positions that come with worry and uncertainty about what happens next. This is somewhat known at least in the UK academic sector. But there is another layer that we are only starting to talk about. And this is parenting and its effect in academics. The lack of sleep that doesn't let you perform at your best, the ability to travel that sometimes is very, very complicated, especially when your children are young. And this constant thinking that never, never switches off, this mental load that never switches off. And for international members of staff, there is yet another layer. Visas tied to short-term contracts. That means that we need to renew our visas constantly, and this brings additional costs due to the nature of our migration status. We sometimes are not able to access some support systems, particularly childcare, that can be quite expensive. And being away from home, most of us don't have the family network that is often there to support raising children. If we only see the CV, we miss the context where people started. And sometimes I wonder, what if our CVs included where we started, the support systems we had access from? Because the place and time we are born into define these characteristics. Having those in a CV will tell a lot about a person's resilience, commitment, and tenacity. I'm extremely grateful to my parents. They've always been supportive and loving throughout my whole life to bring me where I am today. And my family continues to be my foundation. My husband and my son supporting me to be growing my academic career. What can we all do to make these aspects more visible? Start with empathy and understanding from immediate peers, managers, all the way to institutional leadership. Because awareness is the first step towards better support, better policy, and better systems. Also, be a leader. You don't need to be in a position of power to do something. Even a small action in your day can make a difference. This can make our spaces, our environment more aware, more inclusive, and more human. And for your academic journey, persevere. Follow your passion. You have your north is your passion and your purpose. And don't worry, life can be messy, and that's okay. That's part of learning. That's what we call the learning curve. Be curious. Explore beyond your comfort zone. You may be amazed of the things you can do. You can end up talking in a radio show. And finally, you're not alone. Find your community. Because research can feel particularly lonely, but it doesn't need to be like that. For me, I found a range of communities around that have helped me thrive and carry on doing the things that I love and contribute to my society, contribute to the world. And everything that I've shared is not just because I've done it myself. I've had the opportunity to meet amazing people that have supported me to be where I am now. And while I'll continue my journey, I'm very happy to contribute in my capacity to make this place a better world. Keep in touch. You can reach out to me. You can find me on LinkedIn with my name, Isabel Pazmiño Mayorga. And as this is a recording after the actual talk, I had a few notes about the questions I had that I thought would be very interesting to share with you now. One question was about how do we combine interests, additional activities with time constraints? And my thoughts on that are that yes, you should explore beyond your comfort zone, but also look at yourself in the inside and see what you're good at, the skills you already have, and exploit those that you're good at, that are easy for you to do, and that will make things much easier. But when you feel the heavy weight of something that you don't love, you don't like, and you're not good at, perhaps it's something to reconsider. You can always explore, discover new things, but it's always important to give a check on the things that you enjoy the most. Another question I had was about if I've ever had a mentor and what was his or her impact in my journey. And yes, a mentor is a person that is more senior to you, that has more experience, that, let's say, has been in your shoes years ago and has walked a bit more and is in front of you. And I had a mentor when I was a recent graduate. He was one of my lecturers at the Escuela Politécnica Nacional, and his support during the early days of my as a recent graduate was fundamental. For example, when having to decide to change jobs, I wasn't sure how to do. My family couldn't support me with that as they were not involved with the engineering world. And he only asked me a few questions. For example, what do you do after work? That for me was a bit weird, but actually that helped me realize that your life is not only work, it's also the passions and the things that you like to do outside of work, and see if the new job that I was offered will adapt or adjust to my interests, my life interests, not just my work. And a final question was about if I'll be talking in the future or if there is another talk coming next. And yes, I have very exciting news. With a colleague, the one that you see in this picture is the lovely Elena. She is a colleague here at the University of Manchester that I met her in the first place through Toastmasters. And we are developing a workshop to be delivered as a science communication conference. It's the first science communication conference I'm attending, and I will be one of the facilitators. And I'm very excited contributing now to the science communication world. This is the end of my talk, and I really wish that you enjoy what you heard, and this gives you a bit of a flavor of all the things that are outside. If it inspires you, if you would like to get some ideas, or if you feel stuck, look around your community. If you don't find a community, you can always start one. Remember, you are not alone. Thanks for watching. I'll see you very soon.